let's get started. So I just want to quickly summarize what we talked about last time. We set up the Markov process. The basic thing we dealt with was the push forward of functions. It's a time homogeneous Markov process, just to be clear. And so it pushes it forward, meaning it's the expected value of f of x. Let me fix this typo. Okay, so PT pushes the function forward in the sense that if I start the initial condition at x, then the Markov process evolves at time t to state capital XT. And then it's a conditional expectation of that function, of the function value at that point, given this initial condition. So that is PTFT evaluated at little x. PT of f is just for any positive. These are all possible initial conditions. That's the way to think about this. Okay, so I'm just pushing this function forward, and as we talked last time, it's a smoothing operator. Okay, then we have the dual of PT, which is PT star. This inner, we talked about what this is really not an inner product, just a representation, but we know what this means. This is a dual. PT star operates on measures, and similarly, we have got the semigroup generator, which is if I take the push forward operator, is the derivative of that in this sense. That's the generator. And then the adjoint of that generator is L star, which operates on measures. These are the four operations. Yes. There are issues about this thing. I'm just ignoring what L is defined and not defined. In fact, I will not even usually use it on measures. I'll use it on densities. So that's the way, if you remember the way in notes 3 we dealt with it, we just did everything with just density functions. And L star actually, so there is a way of dealing with it so that L and L star can be done just using Hilbert space duality without even worrying about any of this stuff. Because you can think of a density function as just a function. And then, yes, it restricts the spaces in some way, but I'm not too bothered about the technical details for this class. Just want the idea, so I'm going to be sloppy. Okay. So the second thing, I've changed the notation. As Gustavo pointed out, my U looks like a mu. So I call it a H this time. Hopefully it looks very different from the mu. So it's HT is PT of F. So then this is a function. This is the smooth version of F. Okay, F is the initial function. I push it forward in time. I get a smooth version, which is H. And the random variable underneath this whole thing is XT. And suppose that one's measure is mu, then we have the two equations. The Kolmogorov backward equation says how does HT evolve? That is del by del T of HT is the semigroup operator or semigroup generator operating on HT. And the time derivative of the measure is the L star operating on mu T. Okay, and we saw in terms of densities, this is just a density. This is a density evolution equation. This is the conditional expectation evolution. Okay. And so this is a summary of all the objects we saw. Today we are going to use these objects. So this summaries, I'll also post a summary sheet somewhere on the Dropbox. I just wrote it now, so I'll put it in the Dropbox.
So the back equation, before we introduced the semigroup and the generator, how did we do that? What did that look like? That was
this. I didn't understand.
This is the thing that you derived, and you gave.
We derived both of them. We derived this first.
Yeah,
so
you did this yesterday, right?
All this is yesterday.
But you also, for the simpler case where we were just instead of
we didn't even bother to do this. So we did not do this side at all. So in the simpler case, we simply studied the density evolution straight. So I never even introduced this. We directly just derived this from first principles. Okay, because the goal was to just study density evolution. But the more formal way is to start with the forward equation, which can be derived straight, and then do this dual trick to get to the backward. Start from the backward equation and do the dual trick to get to the forward equation. That's how we did this for.
Just the definitions.
A little bit more than a definition. Yes, effectively. It's a definition of L, effectively. Okay. All right. So this is a summary of where we were. So now let's get back to the claim. I'm going to restate this claim since I'm not going to prove it, but let's just look through this once more so that we are comfortable, and then we'll get to other stuff. The claim was for the standard OU process, which is just dxt is minus xt dt plus root 2 dbt. What happens? So first, the stationary measure, the invariant measure is just a Gaussian zero mean into variance 1, because I'm just doing the scalar case here. We have, and this, all these use this explicit x for this equation. There's an explicit way of writing xt, which is what we talked about. The explicit way to write xt was to say that you can equivalently think of it as some x0, which is exponentially deviated in time, plus some independent random variable. This is just the Brownian motion sampled at this time, which means it's just, it is simply a Gaussian with mean 0 and variance equal to this. Because remember, a Brownian motion at time s is just 0 mean variance s. So the time here is e to the 2t minus 1, so that's the variance term. Okay. So it is just this mixture of this initial condition and this, that's xt's distribution. And so if xt, the initial condition itself is a Gaussian, then we know that any, and these are independent Gaussians. So this is just a linear combination of two Gaussians. Is this correct? I think, yeah, okay. We can rewrite this. Let me look at the cleaner rewriting. There's an e to the minus 2t. Is this e to the minus t? Give me a second. Yeah, I guess that is correct. Okay, fine. In any case, it's a linear combination of two Gaussians. So you can actually explicitly figure out what the variance is. And if you, let's just make sure this is correct, okay? So this one is E. If I look at the variance, the mean of this is the sum of the means, which is 0. The variance is this one square, e to the minus 2. Oh, okay. It's e to the minus 2t plus this also squares, e to the minus 2t, and this is e to the 2t minus 1. So this cancels, it gives you e to the minus 2t, e to the minus 2t. This is 1. Okay, so this is all correct. Good. So this is indeed correct. And xt also has a variance of 1. Okay. We wanted to show all these things. The key thing we saw was Stein's lemma, which basically says that a random variable is a Gaussian if and only if the expected value of z f of z is equal to expected value f prime of z. And now this is for all continuous bounded functions f. So instead of f, if I put in the function, if I replace f by a new function g prime, this becomes g double prime. So then another way of saying it is z g prime of z is expected value of g double prime of z. And if you, once you look at it this way, you see that this difference is essentially the semigroup generator applied to z, meaning the L for this process is just z times g prime minus g double prime. Okay, when I apply L of g. So again, I'm just summarizing what we did last time. So equivalently, z is a Gaussian if and only if the generator applied to g of z is 0 for any g. Okay? That's another way of thinking about a Gaussian. This is sort of the beginning of Stein's lemma, which is used for many other things beyond this. But we are going to use this for deriving all the calculations about. I'm not going to go through these calculations once more, but essentially all four pieces of this lemma use this. I think three of these parts use this Stein's lemma to actually prove it, and we did this last time. Yes.
Examples where it's also used as nicely? Because when I see G double prime and G and then a Z, I'm just thinking of e to the x squared, and it's just taking down, it's just a chain rule of that, but it's preserving the main function.
I'm going to, let me not digress. Yeah.
I just mean, is it a special trick that is basically only useful for a Gaussian?
No,
or
the Poisson, I can do it for Poisson. In fact, I have lecture notes on how to use this. In the concentrations class, I do this.
that I basically did G itself back?
So essentially, one generic way of one generic machinery that has been used a lot is the following. Suppose my problem is, I want to show that something is close to a random variable Z, not necessarily a Gaussian. Okay, I consider, for example, a dynamical system, or I want a limit theorem, and I say that the limiting random variable is Z with some distribution. Okay, the classical way was to sort of show asymptotics and show that the error goes to 0. The more recent way is the following. You construct a Markov process, whether it's discrete time or continuous time, whose invariant distribution is what you care about. Okay, the Z, not necessarily a Gaussian. It could be an exponential, for example. Okay, then, or it could even be a delta function in some case for deterministic convergence. Okay, this is a paper by Laying and others for the delta function thing. Once you have this Z, now look at this Markov process and look at its generator, and now say, hey, we know that for any function f, L of the one characterization of that Z is if I give you a test random variable W, okay, now you give me a test random variable W, let's call it Wn or something like that, okay, because it's some finite sample approximation or something like that. Let's look at this random variable Wn. Then you apply it and ask, is it true that expected value with respect to the known distribution mu, which is what you want, of, sorry, not with the known distribution. W has some measure. Look at expected value of L. L is the Markov process which truly has the invariant measure of mu. Is expected value of L of W equal to 0? Okay. It likely will not be. But then if you can show that this is small, that expected value of L of W is small, then this implies that the Wasserstein distance between Z and W is also small, and you can get explicit bounds. So this is sort of, I've sort of sloppily but summarized Stein's method. So it starts with constructing an L comma mu, and then using that to prove bounds for something else. Okay. And this has been used for exponential. It turns out what there is no single Markov process. Use whichever is most convenient to actually lead to the kinds of bounds you want. So one thing that is used for exponential random variables is the reflected Brownian motion, which is essentially the Brownian motion sent through something called a Skorohod map. Okay. So it can be done. I don't want to go too much into writing all this out, but yes, this has been used a lot. Actually, even for other types of dynamical systems, people have used this, not just for random processes. Yeah. Okay. Okay. So in this case, we are using the Gaussian property, and we have gotten explicitly for a Gaussian what the generator look like, what the measure look like, and so on. In the vector case, if mu is a d-dimensional vector, then the generator would be of the following form. It will be the Laplacian of f minus this is the regular vector inner product. This is in Rd. This is a vector in Rd. This is a gradient. This is just a regular Laplacian of f minus the inner product x times gradient of f. That's the generator. And the Dirichlet form, or the energy, is nothing but the mu weighted 2 norm of the gradient of f. Okay. We saw that previously it was just f prime, integral of f prime square d mu. Here it's the gradient of f 2 norm. We'll come back to this much more today. Okay. Also, more generally, suppose that the density function I care about is no longer a Gaussian, but has this following form, can be written as e to the minus v by z, where z is just the normalizing function. And so then what do you get? You get log of this, means that you just get minus v when I do log of that. And then if I do gradient of log of that, this is independent of x, so where the gradient wipes this out, which will just give me minus grad log v of x. Okay, so so this is where the Langevin dynamics. Then the Langevin dynamics in this case, this is no annealing, nothing, just a straight Langevin dynamics is just minus the vector minus grad log v of xt dt plus root 2 dbt. Okay, so and then for this case, this is a Markov process in RD. So we can show using this machinery that mu of x is indeed pi star of x. That is the invariant measure. The generator for this process is Laplacian of f minus the gradient of v inner product with gradient of f. Okay, I'm putting all this down here so that we'll use these formulas later. I just wanted to collect it in one place. Okay, which in explicit form, the Laplacian is nothing but the trace of the Hessian, which means summation del square f by del xi square. And this inner product is del v by del xi, del f by del xi. That is the generator. The dual is in this case is again Laplacian of pi. So I've written it in the density form here explicitly instead of sort of writing with measures. It's just Laplacian of pi plus the divergence del dot pi times grad v. So again, you see this is exactly what we did in the last time when we did it from first principles a few classes back, that the vector field, the density evolution was multiplied by the vector velocity field, that is grad v, that's the velocity field, was multiplying that, and you took the divergence, and that's basically what was the first order term. The heat term gave the other one. So we did the same thing. You can now see this theory will lead to the same calculations. Okay. The one thing we did not talk about before, which is actually going to be essentially the focus of the second latter part of today's class, is that the Dirichlet form is, for this one, is also of the same form as what we, remember the Dirichlet form in general is nothing but f L of f mu. That is the definition. Okay. When you evaluate it for this particular thing, this is the L, you're going to get this very nice thing, which is nothing but it's just the gradient of f whole square d mu, which is exactly what you saw for the OE process. So we are going to call this energy all the time. Yeah. All right. So I just put all this down. I'm going to now switch modes for the next about 15 minutes to introduce a bunch of metrics. So far, we have studied a Markov process and its evolution. If I want to talk about distance between distances in this measure space, I need to start talking about divergences and other metrics for between measures. So I thought I'll just sort of segue and talk a little bit about that, and then come back to the Markov process discussion. Okay. So, and in this process, I want to introduce few other ideas which are going to come back. We'll revisit again and again through this class in several lectures. Okay. So, in a Langevin dynamic, we know that just from the above discussion that the Dirichlet form is nothing but grad f square d mu. Okay. Now let me introduce the first distance, which is the Fisher divergence or the Fisher information distance. Okay. The Fisher distance between two measures mu and nu is nothing but the grad log d mu by d nu square dx. This is just, okay, what is d mu by d nu? If densities for mu and nu exist, this is nothing but the ratio of the two density functions. In general, it is formally the radon-Nikodym derivative. But for anytime you have a density, it's just a density ratio. But formally, I should just say radon-Nikodym. All right. Suppose that, so let me try to look at this a little bit more. Suppose that mu and nu are, let's say that the radon equilibrium derivative or the density ratio is f. Let's just call that as a function f. Okay. Then you see that this Fisher information between nu and mu is nothing but the Dirichlet form of f with f, the energy of f, essentially. Okay, that's just by observation. This is the definition. I'll just put this as f of x, and then from definition, this is just gradient of f squared d nu. Okay. Okay. So, and when I put some f here, this is something like a score function. Okay. If the density happens to be with respect to the Lebesgue, then it's essentially a score function. Okay. Yes. Grad log, what did I grad f? Okay. Maybe you're right. Thank you. Let's fix it. Thank you. Actually, that's a good point because I'm going to look at it as density differences when I do it later. So yeah, good. Yeah, that's a mistake I'd written here. Thanks, fix. In this context, I'm going to show you some relationships which are interesting. I should have written the definition of KL divergence. I figured all of you had seen KL, but I should have written it anyway. I'll fix these notes later. I'll write this on the board for now and write it later. Another distance between measures is a KL divergence, which is the integral correct? I always get this wrong. So I think this sign is correct now. Okay, good. So the KL divergence is nothing but the integral of f d mu now that the f is nothing but log d mu by d nu times mu. This is another way that you have seen in several other classes to look at distances between distributions through this divergence. Okay, so you could ask, so there's a really beautiful relation called De Bruyn's identity, which relates the KL divergence and the Fisher information. And by the way, I'm introducing all these objects because at some point we are going to say, you have a time varying distribution trying to converge to a stationary distribution. You can ask how close are they? As the Markov process evolves, at any point in time, xt has some density function, and then the stationary distribution is something. So I want to start talking about how close these two objects are. So I could look at it in different ways. One way is to the KL divergence. Another way is to the Fisher information. And we want to go between these different things. And so that's where these identities will play a role, which is why I'm introducing all this right now, and we'll bring these things back. Okay. The first is this thing called De Bruyn's identity for divergence, which says that if I take two random variables, y1 and y2, and we'll prove some version of it sometime downstream. Right now, I'm just stating the result. If I take two random variables, y1 and y2, and smooth each one with a Gaussian, meaning I take a Gaussian z theta with mean 0 and variance sigma square, theta square. Okay, this is independent of y1 and y2. So y1 smooth by z theta is mu theta, y2 smooth by z theta is nu theta. Okay, so these are both the smooth versions of these distributions. Then, with respect to theta, the KL divergence between mu theta and nu theta is equal to the negative of the Fisher information, Fisher divergence between these two. Okay, this is called the De Bruyn's identity for divergence. Actually, this version was proved by Andrew Barron in the 80s. Okay, in annals of problem. Yes, the setting is mu, y1 is any distribution, y2 some other distribution. And the theta versions are the smooth versions of those two. Okay? Gaussian smooth version of them. Then you can do this. And actually, I think there's if I'm on record, but I think there's a version of this from Krishna Narayanan has proved a version of some other version of it without Gaussian smoothing. I'm pretty sure, but yeah, 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 yeah. So this is from early 2000s, sometime then. But I'm just sticking to the Gaussian smooth version of this stuff. Okay, so there's also instead of looking at it between two distributions, you can look at it with respect to just the Lebesgue. I can just look at it one of these things, which means with respect to the Lebesgue. Okay, which means the Fisher information is nothing but the grad log p, the expected value, where x is sampled from mu. So this is nothing but the expected value of the score square, the score function. So you saw the score function played an important role. Now you're seeing the score function itself comes as a particular information metric of yeah. Similarly, we have entropy, which is just negative log of the density. And Fisher and entropy are related to the original De Bruyn's identity. So this is the original identity, which is that the derivative. If I take a distribution and smooth it with a Gaussian, just as before, and then you ask if I change as a function of the change perturbation in the variance, how does the entropy change? It's equal to is equal to the Fisher divergence. I think there may be a negative sign. I'm not sure if there's a typo or maybe not. I don't remember right now. Okay. It should this side has a negative because the KL is okay. Yeah. Yeah. Okay. So this is correct. Thank you. So this is the De Bruyn's identity for entropy. So again, I've just introduced these objects out of nowhere, essentially right now. We'll start, as the semester progresses, you will use these things and you'll get a better sense of these, what's going on here. I will skip this final relation. I'll bring it back when I actually need it. But I want to show you one more interesting thing, just to get a sense of how KL versus Fisher looks like, just to visualize things. Okay. This picture is, I think, interesting, and I should thank Advait for helping me with this. Advait Parulekar is a student here. So suppose I have a mixture of two Gaussians. Okay. So P of x is it's a mixture with the mixture weight being alpha. So this could be, if it's 0.5, these two are 0.5, it's two Gaussians at -10 and +10, it's scalar case, equal heights. As alpha is 0.9, so there are three colors plotted here. This is at -10, there's a Gaussian of 0.5 component size, 0.6 component size, and 0.9 component size. And therefore, on the other side, the 0.5, 0.4, and 0.1. Okay, they are two it's just a two mixture model. Okay. So if let's plot the score function of this, which means grad log of this density. Okay, so the score function looks like this. Okay, for this problem. Let's zoom in, because there are three score functions here. If you look at it, the score functions near zero. As I change the mixture weight, the score function shifts. Okay, but far away from zero, it's very, very hard to see anything to distinguish. Those lines are essentially on top of each other. They sort of are different near zero, but far enough away, they all are just essentially slope of -1 or +1. Okay. Okay. So this is how the score looks like. So now let's look at how Fisher is going to look like for this. What are you doing for the Fisher? You're taking the score, you're squaring it, and averaging it with respect to the base distribution. So all these three distributions essentially have no mass here. Okay. They only live here. Yeah, there is some tiny mass here, but there is no mass anywhere here. Okay. So if I average it, then it doesn't matter what the mixture weight is. all of them, the Fisher divergence, the Fisher is going to, if I look at therefore, if I look at the Fisher divergence between any two of these distributions, say P.5 and P.9, it's going to be close to 0. The reason is, again, time, it's a log there. So when I look at the log of the density ratio, it's log of the first density minus the log of the second density. When I integrated these two, when I integrate with either of these measures, they both are going to be roughly the same because they will only pick up these functions over these regions where the density is large. Far away, it doesn't matter whether the functions are same or different, which means a Fisher information will not really discriminate between mixture weights. It will get the, so if you, so this is the intuition you should have when you're getting convergence in respect to Fisher. You should get basically, and you're saying the underlying distribution later on we'll deal with, it's a multimodal distribution, then it's not going, it will not pick up, it will not weight the modes correctly. All it will say is the mode components are correct. The means are aligned and the covariances are aligned. But what the relative weight for various modes is, the Fisher is too weak to actually pick it up well. Okay? Whereas the KL divergence will actually pick it up because it's actually measuring the difference in the densities itself. Okay? There's no gradient there. That's the key thing. And if you think about it, essentially, if you take the x is, if I take a gradient, suppose this wasn't there, then this will just be a constant. And whatever this weight is shouldn't play in a gradient. And far away from this mixture component has a mean somewhere near 0. Yeah, if there's imbalance, it's pushed here or there. But it's, so far away from the mean, only one component really exists. The other component is effectively 0. And so the Fisher is not going to capture that. The KL, so KL is, in general, KL and Fisher are not comparable, but in the kinds of problems we care about, where we have sort of underlying distributions multimodal, okay, we should have the intuition that a Fisher is much weaker and can, in machine learning applications, could lead to more, it will not capture mode collapse correctly. Okay. This is something we need to keep in mind, and all these will become somewhat clear when I come back to VAEs, GANs, and posterior sampling and all that. Okay. But this is just a heads up on, I've given all these equations, and so this is a look forward in a few weeks. Yeah.
Why is the score the same here? Like each of the
Okay, this is roughly the same. Okay, look at that density function as a function of alpha. I'll give you a hand wavy argument why. Far away from 0, for whatever value of alpha, this will look the same. Okay, you don't need to worry about 1 over p and p. Just fix a single p as a function of alpha. Okay, let's look at it far away from the mean. So out of the two components, only one of the components is there. The other component doesn't even exist, because it's exponentially smaller than the other component. Because one is, if you're this side of the mean, the other is so much further away from the other mean. Okay, so it's just one component. So say it's e to the minus x minus 10 whole square. Let's say you're far in the positive. Okay, it is 1 minus alpha times e to the minus x minus 10 the whole square by 2 sigma square 2. That's how the density looks like. Then I take the log, it becomes log 1 minus alpha plus that thing, and I take the derivative, it kills it. Okay, that's the intuition why Fisher kills mode weights. Does it make sense?
Yeah.
So again, this is strictly not the equation. This thing is the intuition you should have when we say we are showing some Fisher convergence versus KL convergence. You should realize that they actually mean something in terms of the underlying system. They mean very different things. All right. So this is all I wanted to say right now for about just metrics. We'll worry about we'll now start proving theorems about these things, and then we'll start interpreting it in a few lectures. One other thing I'm not going to talk about in the lecture notes, but it's there I'm not going to talk about it in class, but it's there in the Dropbox, is the proof of Stein's lemma. So why is it true? I said that for a Gaussian, it's true that Z is Gaussian if and only if L of f of Z is 0. And there's a note here proving this Stein's lemma. But since it's too much of an aside for this class, I don't want to actually prove it in the class. But I've just put it in the Dropbox so you can read it at your own leisure. Okay. So we have at this point, built up the following machinery about Markov processes and something about distances between measures. We have these two pieces of things. So we'll start pulling these things together. Okay. So right now I'm following Ramon van Handel's Probability in High Dimensions book. So in this note and the next note, unless I otherwise note, whenever I say mu, I actually mean mu star. Okay. When I deal with something which is not mu star, I'll put mu 0 or something like that. Okay. So the setting we have is, we have a Markov process with generator L and invariant measure mu. And I want to talk about the Poincare inequality today. So it relates essentially the variance of a function with the Dirichlet form. Okay. So let's put those T equations here. So in the Gaussian case, the Dirichlet form is gradient of f square with respect to the L2 mu norm, which means that it is just this sum of gradient squares averaged over the entire, or averaged with respect to the distribution. The variance is what it is. You know? And the Gaussian Poincare inequality states the following, that the variance is less than, the variance is bounded above by the Dirichlet form. Okay. That's the Gaussian Poincare inequality. Okay. This thing is fundamental. As we'll see, this inequality is fundamental to understanding how Markov processes converge. But for many of you who have taken my advanced probability class, you have seen a Poincare inequality in something called the Efronstein inequality. This also plays a fundamental role in concentration of measures. Okay, so let me just flash to that particular note because I see so many people in this room who actually have taken my other class. So when we did tensorization of variance, so the Efronstein inequality said the following. So if I had a function of IID random variables x1 through xn, okay, pick any one component xi and replace it by an independent component xi prime. And then let that random variable zi prime. So it's an n coordinate system. In one coordinate, I just put an independent version instead of instead of xi prime. That's zi prime. Then the Efronstein inequality said that the variance of z is less than or equal to half times the sum of zi minus zi prime whole square. We derived this. I'm not going to derive this in this class, but I want to just show the connections. This is sort of like a discrete difference. Okay, it's a one coordinate. It's a sum of quote unquote gradient square. The variance is bounded by the expected sum of the gradient square. Okay. And this is where we started. We showed that starting from this, you can show various other things. You can get concentration out of this business. Okay, you can get sub-Gaussian concentrations out of this style of thinking. Okay. So it's the same thing that it turns out that the same relation between variance and the Dirichlet form actually plays an important role in Markov chain convergence as well. And that's the direction that we are going to discuss today. Okay. So let me state the theorem. Let me discuss it. I don't know whether I'll complete the proof today. I suspect not. But I want to spend some time just discussing the implication of the theorem before we actually get to proving it. Okay. So suppose PT is a reversible and ergodic Markov process. Let L be its generator and the invariant measure be mu. Then the theorem states that the following 5 statements are equivalent. The first, for any function f, the variance of f is less than or equal to c times the Dirichlet form. Okay. That's statement number 1. Statement 2 is that this Pt of f minus mu of f in the L2 norm. So what is this? Just because we have thrown so much notation at you, you notice that this is just nothing but the variance of the push forward. Okay. Meaning, let's start here. This is the variance of the function because f centered about its mean averaged. So this square of this would be the variance. So this is the square root of the variance. Do you agree that this is this quantity here, which I've underlined in red? If I squared it, it would just be the variance of f. Which means, let's look at this. Think of this as the function g. Mu of g equal to mu of f because I'm starting from stationarity. Okay, so the distribution of xt is identical to x0. So mu of g is the same as mu of f. So that means this side is simply the variance mu of pt of f whole square. Okay, the square of the variance. So this statement is saying that the variance. So if I take a function and I push it forward through pt, it is our intuition from last class was it's getting smoother. This is saying that how it's going exponentially, that variance is actually coming down and it's coming down exponentially in time. Okay, that's basically what this is saying. Okay? And the constant is 1 over c. And this constant is exactly the same as that of the Poincare. That the variance, if you can show that the variance is less than c times the Dirichlet form, this implies that the variance of the push forward of the function is exponentially decaying in time. This is also equivalent to the following. Look at the Dirichlet form of the push forward function. That's exponentially decaying at rate exponentially in time with a constant 2 by c instead of 1 over c. Okay. The initial Dirichlet form at any time t. So it's telling me how these are all measures of how the function is smoothing over time. Equivalently, you can say given any function, there is some k of f such that the square, if I square this, would be variance. So this is nothing but the square root of variance is going down as e to the minus t over c. This, of course, implies this, but because here I've explicitly told you that the initial condition is this variance. But I just want to, for completeness, write 5 statements and show that any one, if you prove, then all the other 5 hold, all the other 4 hold. And the 5th statement is the same with the Dirichlet form. The Dirichlet form, for any function f, there is a kappa of f such that the Dirichlet form is going down exponentially in time this way. Okay. So this this is characterizing the variance of the function going down. You may want something stronger. You may actually want the KL divergence to go down. We'll get to that in a couple of lectures. But I want to start with a variance statement. This is saying the variance of the function, push forward of the function, exponentially going down in time, if and only if the Poincare inequality holds.
Sanjay, this is related to mixing time as well, isn't it? That C has to be related to that, no?
For people who have sort of played with the concentration side of the story, you saw that we started with we got a variance bound, which was the Efronstein, which effectively implied sub-exponential concentrations. And then we did the log Sobolev inequality then, and which got you sub-Gaussian concentration, which is e to the minus x squared instead of e to the minus x. Here again, we're going to see the same kind of story with Markov processes. This is essentially an exponential, this is a variance term going down, and then we'll get a K, with log Sobolev, we'll get in KL divergences. Okay. We're going to get that. Huh? No. So okay, let's go back to this. Let PT be any reversible ergodic Markov stationary time homogeneous Markov process with generator C and invariant measure mu. This statement is true. So this is, the Gaussian was just an example. Now I'm off of Gaussian. Okay. We'll do the calculations for Gaussians to give. Again, I'm going to go back to Gaussians to show what all these mean explicitly, but this theorem is in generality. Okay. And we will prove the general version, yes.
4 versus 2, how are they getting it?
2 is an explicit form of 4. 2 says the K of f in 4 is this. That's all. The proof is one line. but sometimes you may not be able to, but you may just be able to prove there exists something. So why is these 5 statements useful, you can ask? Yes. If you can prove, this is not, this statement is not saying any one of these are true. It says if any, it doesn't say anything about truth of any statement individually. It's basically an equivalence between 5 different statements. So, yes, then it has, yeah, exactly, all this. Okay, now it says that as long as you can prove any one of these 5 things, all the other 4 hold. Okay, if you can show an existence of kappa of f, then that must be this. Right? So okay. So these are the 5. These are the 5. Yes, you wanted to say something.
One of them is for all f for the other, or is it like I pick an f and
Yeah, pick an f. Choose any f for that f. Yeah, yeah. No. No. You need to show any one of them for all f, then the other things hold. It's not an f by f test. Pick any f in this class and show a statement. So the class f being bounded whatever functions. Choose any f in that class and show any one of these statements for all the f in that class. Then all the other statements also hold for all the f in that class. That's the way to interpret the statement.
If I prove 4, how will I prove 2 from 10?
I'm going to show you that. I'm going to do the proof. I'm going to prove all these equivalences over today and next class. Okay. But first, I want to make sure we all understand what this statement is. Before we prove it, let's do two discussions. The first is, let us assume that let's center the function such that it's mean 0, because I don't want to carry around a mu of f for just this discussion. Okay? Meaning, x0 is sampled from the stationary distribution mu, and I'll assume that the expected value of f of x is 0. Okay? Mu stationary, meaning at any time t, xt is identically distributed as 0. And I'm still in RD case, I think. Yeah, I'll be in the RD case. None of this discussion needs to talk about R. And ht is the push forward of the function f. So ht of x is f of xt given x0 is little x. It's a push forward. So it's an ergodic Markov chain with invariant measure mu. So in this setting, h0 of x is just f of x itself, and h infinity of x is just 0. We saw that this is what we discussed last time. It will just go to mu of f. In this case, I've assumed is a 0 mean function. So if you push it all the way to infinity, h infinity of x is equal to 0 almost surely, mu almost surely. Constantine?
Yes.
Okay. So this is not a statement about this is a statement about the conditional expectation as a function of the initial state. But all this is saying is, starting from the initial state, it will go to the same point everywhere. And since the mean is 0, that the limit should be 0. Yeah. Okay, so we understand about h. Now let's look at mu of ht, which is the same as mu of pt. Okay, pt of f. So we'll see that it's also 0, which is because of stationarity, because mu of pt of f is nothing but ht of x0. This is a push forward in time with this initial state. But iterated expectation, ht is nothing but expected value of f of xt given x0 equal to x. I guess for the conditional expectation, I shouldn't write it this way. I should just write this. Okay. This random variable, it's the expectation of this random variable, which from iterated expectation, I can just combine these two, which is nothing but the expected value of x0 in mu of f of xt. But xt is identically distributed at x0, so which is just 0. So mu of pt, mu of ht is 0 in the average. So this is a much stronger statement than this. This is saying actually it's almost surely equal to 0. But this says on an average it's just 0. It's a much weaker statement. Okay?
But at infinity, it's not.
At infinity, it's not. Yeah. So I mean, I'm just saying all this so that the notation of things are clear. That's all. It's all pretty clear once you have unraveled this notation. But now, let's look at the L2 norms of HT. Okay. Now, this is not an L2 norm. This is an expectation. If I look at the L2 norm, then it's nothing but the expected value of ht of x, the whole square, okay? Starting with x0 is mu. And of course, this is not 0. This is something else. Except at infinity, because this function itself identically 0, the L2 norm is also 0. But you've gone to infinity. Okay. So now let's look at how does the 2 norm go to 0. And that's what the Poincare inequality says. And all it says is the 2 norm of ht is going to 0, or the variance is going to 0, because it's centered. And going down with rate 1 over c or 2 over c. This is, I think it's 1 over c, not 2 over c. I think there's a square. Okay, so that's why it's a 2 over c. Okay? It's going down as 2 over c. It's going down exponentially fast. But now you can ask the following question. So far I've said nothing new. I've just restated what we said in the theorem statement. I just said that once more. Okay. But now let's ask something else. So asking about the 2 norm, I can ask about the q norm. Okay. Meaning, what do I mean here? That means this to the power of q, 1 over q. Okay. So this is now, you know intuitively that as q increases, ht will become peakier. So it's acting against the smoothing, okay? Because higher norms basically make functions peakier. Okay. So for a fixed t, as q increases, HTLQ will become larger. Okay. But for a fixed q, well, we have just shown for 2, but presumably a similar result holds for q. Okay. For a fixed q, as t increases, the q norm will become smaller. Okay. So you can ask, what is this what is this trade-off? And this trade-off is Gross's hypercontractivity theorem. Okay. It says that if I look at the p norm of f, then how much can I bump up the norm so that I still get the higher norm function smaller than the lower norm version? No, there's a t here. This is the t. For some time, so there's a time in the future. This is the higher norm. There's a t norm. There's a function f. I pushed it forward by time t. So I've smoothed it somewhat. I've got ht. But then I've bumped up the norm. So I made it peakier. But I don't want to bump it up too much, because then it'll become too big. How much can I bump it up so that this inequality still holds? And the answer is that it is linear in p. This is the thing. It's 1 plus p minus 1 times 4t. So it's p and t are in this norm. You can see it's t times p. It's linear in time. Okay. So as you go further and further in time, I can make. So let's put p equal to 2. Okay, for this, just doing this calculation. Okay, for this special case. Then if p equal to 2, then this is just 1. This is just a 2. So it will be 1 plus 4t by c. Okay. As time progresses, this is how I can push the norm up without me making the function norm bigger than the original 2 norm, for example. Okay. So the Markov process is so this notion of hypercontractivity is, if you want to see the notion of hypercontractivity in the concentration case, you remember from my other class last semester. I'll give you access to those notes as well if you're interested. So you can see that essentially there again, there's an interaction between sort of polynomial functions which are smooth. And so how can I go between lower norms and between lower moments and higher moments? So in the Markov process case, there's this interplay between norms and sort of smoothing over time. Also, there is this something which I really liked. I want to just cite. Jalil Shafai has a series of blog posts which are really illuminating. I think it's worth reading. It's called Log Sobolev and Bakri Emery. And there are a bunch of other notes as well. You can sort of go down this road much more if you're interested. The point of this class is also to give you pointers to where you can sort of deep dive where you want. And yeah, this is a great resource. And then if you want to understand hypercontractivity and concentration, connection to Bonomi-Beckner, Nelson's theorem and all that, I have a different set of notes. Not for this class, but I'm happy to share that offline. Okay, second question. So this is one thing. This is the norm versus sort of smoothing trade-off. There's a second question you could ask. So I just put the variance is going down exponentially after smoothing. Okay. But this Markov process is started with a stationary distribution, and then I'm pushing it forward all the time. The distribution is stationary. A different question you may want to ask is the following type of question. I want to start from some state x and ask how quickly does it go. Okay, meaning for any x in RD, I want to look at this push forward this function, but with starting with this x and asking. Whereas if I go to time infinity, you know that the initial condition doesn't matter. Though I just put it here to make things consistent looking. Okay, and look at this difference. Can I say anything about this? This is the push forward function evaluated at little x, and mu of f. What happens to this one? Okay, this is as a function of initial condition. I want to understand this smoothing. What we have shown is a soft version of this, right? We are basically looking at this averaged over the stationary measure. Then that is indeed exponentially going down. That's another way to think of anything we have sent so far. So we could, so if I want to, so that's why this p norm so we could ask, instead of x, we could ask the max or the soup or something like that, max over all x. That's a much stronger statement to ask. Okay. So p norm is indeed somewhere in between. You know that as p becomes large enough, it's approaching the soup norm. So I could ask maybe statements for any p norm of these kinds of things, which is sort of approaching this kind of a question. And there are papers. You can see that there is indeed a trade-off. Even from the gross hypercontractivity, you saw that there is some trade-off between norm and time. You can make all this for in much more general settings. You can see sort of Poincare inequality, LP convergence of semigroups, and so on. There are papers on this. Again, I'm not going down any of these things. I just want to sort of give some background on what the literature here looks like. Okay, now let's actually do the Gaussian Poincare inequality. So far I didn't say anything Gaussian. Let's actually calculate things out for the Gaussian case. Okay. So I have the OU process. Its generator is the Laplacian of f minus x gradient of f. The invariant measure is nothing but the Gaussian zero mean identity covariance matrix. The random vector z is just a vector z1 through zd with each component IID Gaussian with zero mean unit variance. Variance one. Okay. So what is the variance of this? The variance. So the for the Gaussian, the original Gaussian Poincare inequality is that the constant is 1, meaning for Gaussians, variance is less than equal to the Dirichlet form. Let me write this in 1D case. I'm just going to avoid higher dimensions. Anyway, this is just a calculation, so 1D is just easier to deal. So remember the OU process in 1D from last time? You had an explicit way to write it, that the push forward of the function is nothing but the initial condition exponentially downweighted plus just take a Gaussian zero mean unit variance weighted by root of 1 minus e to the minus 2t. This is what we did last time. So this is the definition. So let's do d by dx. I'm not doing time derivative. I'm doing derivative with respect to x. D by dt, d by dx of pt of f of x. So the only x appearing is here. So I will get chain rule, f prime, and then this e to the minus t will pop out. So I'll get e to the minus t times this, which is nothing but e to the minus t. This is nothing but pt applied to f prime. That's all this is. So derivative in this case is e to the minus t pt of f prime. So that means the Dirichlet form of pt of f with pt of f is nothing but, we know it's integral of f prime square d mu. So it's just pt of f cutting prime with respect to the mu, the two known. So if I substitute that in, I'm going to get e to the minus 2t pt of f prime, two known. pt is non-expansive, so I can drop it. So it is a minus 2t f prime, which is this, e to the minus 2t e of f. So what we have shown is, this is what we have explicitly shown. This is, we have shown this is less than or equal to this. And therefore, this was not too hard a calculation at all, this particular thing in this case. And therefore, from the theorem we showed, all the other statements are true. Okay. I've given you one way to use that theorem. Okay. You do any one of these calculations, and then therefore the variance goes down exponentially. Of course, I haven't proved the theorem yet. That's the major thing left. But this is true. Furthermore, it says that the constant c is 1, independent of d. So which means, in this case, it's saying the OU process, even though it's in high dimensions, is converging to the stationary distribution at rate 1, e to the minus t, independent of dimension. Of course, you would say this is not very surprising because they're all IAD across dimensions. I'm not looking at the max norm. I'm looking at the average across them. So it is indeed that you may not be, it's not a very surprising result in that sense, right? Because in every dimension is going down, it's going down exponentially. And what this is saying is the variance, overall variance, in fact, is also going down across dimensions. But what is true is that this is true for any Langevin dynamic with appropriate functions. That is the next big thing we need to prove after we prove the Poincare. Okay, that this dimension independent property is true as long as that function v is strongly convex, or the measure is strongly round concave. And this will also lead to something called something which is cutting edge right now in TCS and probability, which is the KLS conjecture. So I'll sort of end this whole line with the statement of the KLS conjecture. TCS is theoretical computer science. Yeah, sorry. Okay. I have about 10 minutes. I can start the proof. Let me do the following. I'm going to give so there's the proof of the Poincare. So what? What happens next? I think maybe for 5 or 10 minutes, I'll just tell the story and then come back and start doing the proof clean next class. Okay. So let's assume that we have these 5 equivalent statements true. Let's go back here. We suppose these 5 things are true. So what? What we are going to do next is the following. We want to study the Langevin dynamic. Now we'll come back to this. We'll come back to just the dynamic where the grad log pi star of xt is the drift field. Okay, and we'll also assume that this is strongly convex with some strong convexity parameter. In this case, what we are going to show is that the Poincare inequality holds with 1 over rho as the constant. We'll actually show that. That's the next big piece. And this is the strong convexity parameter, which presumably doesn't depend on d. So and this immediately from the Poincare says that even in this case, the variance is going down exponentially with no dimension dependence. Okay. And then we will not just show it for variance, but show it for KL divergence, okay, which is called the log Sobolev inequality, which is the analog of the Poincare inequality for KL divergence instead of variance. Okay. The key construction which requires all this stuff is something called the Carré-Duchamp operator and the iterated Carré-Duchamp operator. Okay. again, we'll come back. I'm going to repeat all this once more, but it's worthwhile to sort of see what these objects are and how they play in this story. So if I have, don't look at the screen for a minute. If I have f and g as two functions and ask for what is the derivative of f times g whole prime? Well, chain rule says is f prime g plus f g prime, right? If I want to take, that is, if I do the differential operator on fg, I'll get d of f times g plus f times d of g. I can ask, is the same thing true with the semigroup? If I put L of fg, is it true that it's L of f times g plus f times L of g? And the answer is no. L is a nonlinear operator. Okay, you remember there's a second order, and also something is going on there. So this is not true. But then you can ask, what is the correction? What's the quadratic correction for that? And that's essentially the Carré-Duchamp. It is L of fg is so the gamma lambda Greek lambda or gamma. Wait, gamma. Sorry, thank you. This is gamma. I always get mixed up. Okay, this gamma of fg is L of fg minus f L of g minus g L of f by 2. So it's the correction. It is, if this was actually linear, this would be 0. This is the error in the linear. That's sort of what this is. Okay, that's the Carré-Duchamp. And then we will see a lot about this Carré-Duchamp, but I want to sort of tell a story right now. So, and similar to the Carré-Duchamp, I can talk about the iterated Carré-Duchamp. The Carré-Duchamp, I can now start with the Carré-Duchamp and ask, is that linear? And the answer is no. So I can look at lambda 2, I can look at gamma 2, which is exactly what I did, one more level up. And what is remarkable is the following. If I show that C times gamma 2 is greater than or equal to gamma, okay, that gamma 2 and gamma are of the same scale. Essentially, the ratio is some constant. Gamma 2 by gamma is bounded by 1 by C greater than 0. Suppose you show this, which has nothing to do with, it's a purely algebraic property, essentially, about the generator, right? Basically, you take the generator, you create some structure out of, you know what the generator is, some operator. Then I can create gamma out of it. It's defined as a function of L. Then I can do gamma 2. I can do gamma 2 out of it by doing this once more. Okay, it may be messy, but you can write all this out in terms of L. And then check this algebraic property. If this is true, then it implies essentially a Poincare inequality. Okay, so that is if these statements are equivalent, this is called the Bakry-Emery criterion. This ratio between the iterated Carré-Duchamp and the Carré-Duchamp. Again, this is just a heads up of where the next 2 or 3 lectures are going. So if this criterion is equivalent to essentially a Poincare inequality. It's stronger than the Poincare inequality in the sense that it's true. It's a time way. It's I can look at it's a local in time Poincare inequality. The Poincare inequality, remember, on the one side had the variance. So this is, I don't even need to go to infinity. Okay, and so from this you can get the Poincare. A corollary of this, once we prove this, would be the would be essentially the Poincare inequality. And once you have the Poincare inequality, then you take the Langevin dynamic and then write the L and then check the Bakry-Emery criterion, which means you need to compute lambda 2, you need to compute lambda, all sorts of things need to be calculated. But we know what the L operator is for the Langevin dynamic. Okay, there's an explicit form. So that's why I told you that it's a Laplacian of something minus grad V inner product with grad F. It's just calculus at this point. Okay, so you just churn through the calculus, check that lambda 2 and lambda are related, find that constant, and then everything else is true. That you got exponential convergence and all sorts of things. So that's really the power of the Bakry-Emery machinery. It gives a purely algebraic test for showing something about this dynamical system and the convergence properties. Okay, so that is going to be the arc for the next maybe two or three classes. And then we'll see that this actually implies something even stronger, which is for the log Sobolev inequality, that this thing holds not just in terms of variance, but in terms of KL divergence as well. And the punchline of this whole business is going to be that Langevin dynamics for strongly concave functions goes down, it converges independent of dimension. And now you can ask, what if it's just concave? And this leads to sort of this whole thing called the KLS conjecture, which is Kannan-Lowa-Shimonovich conjecture. It's a central thing. And I just took this figure, which looked very cool from this paper by Intatli and Santosh Vempala. It says that if that so the KLS conjecture essentially says that even if the strong convexity parameter rho is equal to 0, meaning it's not strong convex, it's just convex, okay, then there's still the Poincare inequality holds with a constant which is strictly positive. And so all this, everything I talked about is true. And it implies actually a whole bunch of things. Again, from the paper, that if that is true, then something about hardness of sampling, you get results. You get large deviation results. There's a whole bunch of things in geometry, probability, and TCS that all essentially can be shown to be equivalent to this problem. Okay. So again, I'll come and talk a little bit more about this when we get to this point. For today, I didn't want to start with a proof, so I just wanted to give you the outer story, and then we'll start filling in the details over the next several classes. Okay. All right, thank you.